present intersection theory on arithmetic varieties. It's a topic I worked on with Henri Gillet 20 years ago. I will take the following point of view. We shall consider height of varieties. So this means the following. So X will be a projective regular flat scheme over Z. And the height is the following. When we have Y in X a closed subset irreducible, the height is defined by choosing first an hermitian line bundle on X. So I will explain this terminology in detail. Hermitian line bundle over X. And then for any closed irreducible subvariety of X, we shall have a number we shall denote by HL bar of Y, which is the height of Y with respect to L bar. It's a real number, which was first defined by Faltings in his paper on abelian varieties. So I will spend quite a long time on this. I will give a definition which is by axioms. It will be an axiomatic definition. And then the question will be whether this definition depends on choices. A priori, it depends on choices, and we have to work quite hard to prove that it is actually independent of the choices. So the main property that we shall show is that this is independent of choices. But for defining HL bar Y, which is what I will do today, we have to do a little a few preliminaries. So first, I will consider algebraic preliminaries. So I don't mean that the preliminaries have anything to do with the lunch. So where is là. So preliminaries will be about filtration of modules by submodules. So assume we have a ring A, which is assumed to be Noetherian and commutative with unit. And assume M is a module of finite type. Then one can show that there exists filtration M equals M0 contain M1 contain M2, etc. And maybe MR equals 0. there exists such a filtration for any ring A and any module of finite type where mi over mi plus 1 is of the form A over pi, where pi is the primary dual. So this is a general fact about modules. For instance, a trivial case is like m equals a and pi equals 0. If a is integral, we have a stupid filtration. Now what happens is that for some modules, the pi can be chosen to be maximal in A. M is said to have finite length. When there exists a filtration like y, like the one I wrote over there, so let me give a name to this filtration, call it 1. There exists a filtration 1 such that pi is maximal. So a special case of this filtration is when all the pi are maximal or ideal in A. Then there is a well-known lemma which is so-called Jordan-Holder lemma that you find in the book of Lang, for instance. Jordan-Holder is if M has finite length, R is independent of the filtration. That is, assume you can find a filtration of M where all the pi are maximal, then the length of the filtration is always the same. So this length is denoted L of M. So this is the length of M. Okay? And we have the following easy lemma. Say it again.
Can there be two filtrations in the first all P are maximal and in the second they are not?
Maximal in A and what?
And in the second they are just 5.
In general, they are just primary dual. I say that if I take a filtration where pi are maximal, then the length is forced. Is it clear or not? I say it again.
Je pense qu'elle a demandé si, est-ce que c'est possible d'avoir deux filtrations, un avec des idiots maximales et un avec des idiots pas nécessairement maximales?
Oui, bien sûr, oui. Yes, you have filtration with prime ideals. There are plenty, but filtration with maximal ideals have a fixed length. That's the assertion.
Si une filtration avec des idiots maximaux, je me demande s'il peut y avoir une autre avec
Yeah, you can for a module of finite length, you know that you have filtration with maximal ideals, and they may very well exist on the other end, filtration with primes. But we forget about them.
Okay.
Yeah? Okay? So lemma 2, if I have a short hexachecers, like this, and assume m prime m and m double prime of finite length, then the length of m is equal to the length of m prime plus the length of m double prime. I think the proof is clear. You fix the filtration of m prime by mi such that the quotient are maximal. You fix the filtration of m double prime with the same property, and you take the inverse image in M of the filtration of m double prime. This way you get a filtration of the whole of M with quotient A over pi, where pi is maximal. So the length in the middle is the length of the two extremes, is the sum of the lengths of m prime and m double prime. Okay. Once we have this notion of length, we have a notion of order, which is the following. Well, first we define the dimension of A. So the dimension of a ring is the maximal of the set of integers such that exists a chain of prime ideals of length n, so the dimension, the crude dimension, is just the maximal length of a filtration by prime ideals of the ring. And you have the following lemma. If A is in A, assume the dimension of A is 1, and assume A in A is different from 0, then A over A times A has finite length. So a simple way to define modules with finite length is to take a ring of dimension 1 and divide by some principal ideal. So let's prove it. So consider a maximal chain of prime ideals in A divided by small a times A. And call phi the projection from A to A over small a. I forgot some hypotheses. Assume A is integral. Assume A is integral and the two conditions here, then the quotient has finite length. So consider the map from A to A over small a. And consider the inverse image of this situation by phi. So we have pi contained in pi plus 1, etc. And there's something more now. Now the ideal 0 is a prime ideal. This is a prime ideal since A is integral. If the product of two elements is 0, one of them is 0. So the ideal 0 is prime. Okay, so we see that we have the length has increased by going back from A over A to big A because we have a new ideal, prime ideal, which is 0. So we can say the following, that the dimension of A over A, which is the maximal length of prime ideal in A mod A, is less or equal to the dimension of A minus 1. Because the dimension of A contains this chain plus 0. So we get that the dimension of A is at least dimension of A over A plus 1. Okay? But by hypothesis, the dimension of A is 1. So we get that the dimension of A divided by AA is equal to 0 because of this inequality. What does it mean? It means that all chains of prime ideals contain only one prime. So this prime must be maximal. Therefore, all primes in A mod AA are maximal. So we say that there exists a filtration without any hypothesis for any module. There is a filtration with quotient A over pi, where pi is prime, but now all prime are maximal. So for all A mod AA module, there exists a filtration where the quotient, successive quotient are A divided by maximal, because prime is the same as the maximal. So we get that A over AA has finite length. That is, filter this module by A over pi, where pi are prime, then these pi are maximal. Therefore, the filtration gives us the definition of a module of finite length. Okay. Again, this is something I admitted from the beginning. I admitted the following assertion, that for any module of that type, there exists a filtration where the quotient are A over pi, where pi is prime. This is accepted as a preliminary step. So I applied this property to A divided by AA. Then I have a filtration of this module by A over pi. Pi are prime, therefore they are maximal. So there is a filtration of this by A over maximal, which is a definition of finite length. Okay, so let A be as in the lemma. And since A is integral, we can consider the fraction of A, a field of fraction. And if X lies in K, we define, assume X is of the form A over B, where A and B are in A. We consider what we call the order of X, which is by definition the length of A over AA minus the length of A over BA. By the lemma, this quotient and this quotient are finite length, so we can consider the difference. This is, by definition, the order of X. A very good point. In fact, it does not. So you have to check that it does not. I will not do it, but the fact is that it does not depend on the way you write X. So there are two facts. One, that order of X does not depend on the choice of the writing of X as a fraction. Second, if I take the product of two elements in K, the order is additive. So I will not prove these two facts. So let me give some example. Assume A is local. That is to say that A has a single maximal ideal. And assume A is regular. Which means the following: the dimension of A is the same as the dimension called M, the maximal ideal. The dimension of A is the same as the vector space M over M squared, which is a vector space on A over M. A over M is a field, and this is the vector space on this field. Assume the dimension of this vector space is the same as the dimension of A. We say that A is regular, and we assume it's local. Then the situation is simplified. Then there exists a valuation that is a morphism, a non-trivial morphism. So V of xy equals V of x plus V of y. And A is a set of x in K with valuation at least 0. M is a set of x in A where the valuation x in K, and where the valuation is at least 1. And more generally, Vx equals n if and only if x is in Mn and x is not in the next power of M. So the definition of the valuation is in terms of this filtration by higher order of the prime ideal. So think of function on a curve, and you take as maximal ideal function which vanish at some point. Here you have the order vanishing. So the order vanishing is given by this condition. So in that case, the order of x is simply the valuation. Okay. Can you define what?
You only define the order for one-dimensional ring.
Yes. That's a good point. So let's see. So I guess one has to show that the dimension of A is 1. But a local ring can be of a higher dimension than 1. Okay, so assume if the dimension of A is 1, the order of vanishing is the valuation. I was taking the example of curve with a point. So in general, you can have a higher dimension, and then the order and the valuation will not be, and one of them will not be defined. Thank you. Okay. Okay, let X be an Archean scheme and OX the sheaf of function on X. Definition. A line bundle on X is a locally free OX module of rank 1. So this means the following. That there is an operation from this sheaf OL on L, so a map from OX times L to L, and such that locally, this is just multiplication. So locally, X is a union of U alpha, where L restricted to U alpha is the same as O U alpha. And second, mu restricting to U alpha is multiplication. So locally, we have OX, OU times OU goes to OU by multiplication, and this is the description of mu locally. So in general, a line bundle on X will be a module on OX. Assume now X is integral. That is to say, for any open U in X, the ring OXU is integral. There is a point. In that case, there is a point called the generic point. With residue field, the fraction of function, rational function on X. and we have L eta isomorphic to O of eta equals K of x, because we localize at the generic point, we should get the same as function. This is the assertion here for line model. So maybe someone can say what is the generic point. It doesn't come to my mind all the way. What's the definition?
I guess it's a point whose closure gives you the whole.
Yes. So that's the definition of generic point, a point which is Zariski dense in X. Yes, it's everywhere. It's close to every point in X, so the Zariski closure of eta is X. Okay? So definition. A rational section of L is any element S in the generic point of L. So what happens is that global sections have divisors. I should define what I mean by this. Let Z1 of X be the free abelian group spanned by Y in X, Y integral or reducible, and codimension of Y in X equals 1. So this is the definition. We call Z1X the group of divisors on X. What I claim is that if I have a rational section of a line model on X, I will have a divisor. So let S a rational section of L and assume Y in X as codimension 1, and Y is irreducible. Then we can consider, we know that we have a ring A, which is O of X, Y. So Y is the Zariski closure of a point because Y is by assumption irreducible. So it has a point which is dense in Y. And we consider the localization of A at the point Y, which is codimension 1. So this ring A is local, integral of dimension 1. fractions of A is nothing but the residue field of K at the generic point, so we call it sometimes K of X, is the field of rational function. So now we have a section. We choose a section different from 0 of L at the generic point. This is the same as K star, because L eta is the same as K. Locally, functions are the same as section of a line model. And we define ny to be the order at A with respect to A of the section S. And when you have A of dimension 1, its fraction field is K, so we have a notion of order of S, and this gives us an integer ny in Z. So by definition, the divisor of S is the sum over all closed irreducible of codimension 1 ny times y. It's not hard to see that it does not depend on choices of the trivialization, like on the trivialization of L eta isomorphic to K. So the divisor of S is a sum over y, where the coefficient of y is the order of S with respect to A, where A is the ring of function at the point, at the generic point of y. Other question? So let me give an example. Assume K is an number field. And let X be the spectrum of the ring of integers in K. So giving, we are in the affine case, so giving L is the same as giving its global section. So the global section is the rank 1 OK module, local F3, that is projective. So lambda is a projective rank 1 OK module. And in that case, we consider a section different from 0 of this projective module. Then the quotient of lambda by the submodule spanned by S is a product over all prime ideals in OK of OK divided by some power of the prime ideal P. And this is the Chinese remainder theorem that the lambda over OK of S can be written this way. Then it happens that NP is nothing but the order at OP, of OP of S with respect to the local ring OP. This is what we showed in our example of the order, that this is the same as the valuation. So we get that the divisor of S, in that case, is the sum over all prime P, NP times P. So NP can be computed as the valuation defined by P of S. Okay, so that's the algebraic preliminary I was planning. I don't know whether there's a break or I should keep on speaking for an hour and a half. I could have a break of 5 minutes. And if there are questions. Okay, so now we'll do some analytic preliminaries. So we consider X a smooth analytic manifold over C. We denote by OX and the sheaf or analytic function. And we consider the analog of line model that we had in the algebraic case. So we consider holomorphic line model over X by saying that it is locally free OX and module of rank 1. We also define a metric on L as a set of maps from Lx, which is the line model, which is the the sheaf of local section divided by the maximal ideal. So this is a complex vector space of dimension 1. So for each of these fibers, we have a map to positive real numbers satisfying the following. Well, the norm of lambda s of a section is the absolute value of lambda multiplied by the section S, the norm of the section S. Second, S is equal to 0 if and only if S equals 0. And third, let U in X be an open subset of X and S a section which does not vanish on U, so S in LU which does not vanish on U, then the map X in U goes to norm of S at X is C infinity. So we cannot have it seems that we should say analytic, but analytic is too strong. So for the norm, we just ask that it varies in a C infinity manner. And we take the following notation. A line bundle arithmetic is a pair L of L with a norm this way. So this is an hermitian line bundle. On X. Now we can consider differential form on X. So we write an of X to be the vector space of a C vector space of differential form C infinity differential form of degree n on X. Then there exists a decomposition. An of X is a sum of a P plus Q equals N of forms of type PQ of X where APQ of X is a set of forms of degree n which can be written locally a sum of forms of type PQ U dz1 wedge dzp wedge dz1 dz j1 dz bar gq, so that's I1 IP, where dz is simply dx plus I dy, and dz bar is dx minus y dy. So there is a decomposition of forms of the Guen as sum of form of type PQ for all P plus Q equals n, where form of type PQ are those written locally this way. Okay? Now when you take the differential d from an of x to n plus 1 of x can be written as a sum of two differentials where d maps APQ to AP plus 1Q, and d bar sends APQ to APQ plus 1. What happens is that d2 equals d bar square equals d square is 0. So the three of this d, d bar, and d are differentials. The square is 0. We define dc to be d minus d bar over 4 pi I. And we get ddc equals d bar d over 2 pi I. Okay. So lemma 4 let L bar be an Hermitian line model HLB on X. Then there exists a form C1 of L bar of type 1 on X such that given any open set in X, an S section of L on U with Sx equals 0 for any X in U, so a non-vanishing section, then C1 L bar restricted to U is minus ddc log of the norm of S square. So the first transform is defined as DDC of log of the norm, at least outside the zeros and poles of S, or in zeros in that case. So we can prove the lemma. Say it again. Thank you. S is not equal to 0. So assume we have another section. Then the two sections, because we have rank 1, the two sections are proportional. Then exists a function f invertible on U such that S prime is equal to Fs. So if we consider minus DDC log S prime squared, we shall find minus DDC log S squared plus or minus DDC log of the absolute value of f. Because the norm of S prime is simply the absolute value of f times the norm of S. So what we need to show is that DDC of log of the function is 0. Okay. So compute dd bar instead, dd bar of log f squared. So we first apply d bar. So we get d bar f over f minus plus d bar f bar over f bar. F squared is just f times f bar, so we get that d bar of log f squared is this sum here. And f is holomorphic, therefore d bar f is 0. So this is the same as d of d bar f bar over f bar. But now we can exchange d bar and d, so it's minus d bar d of f bar divided by f bar. And this is 0 because we have d bar f equals 0, and by taking the conjugate, we get that d of f bar is 0. So we have shown that this number is 0. Therefore, the definition of the curvature of a line bundle is independent of the choice of the section taken on some open where the section does not vanish. So C1 L bar is called the first transform of L bar. Okay. So now we have done enough preliminaries to define height. So let X be a projective regular scheme over Z. So if we consider the complex point of X, if X is given by some equation, X is just a solution of this equation with complex numbers. So consider the test of complex point. Well, it will be a regular projective flat variety of a spec C. So this is in particular a smooth complex manifold. It is smooth because X is regular. So smooth implies regular. The converse is not true. But if we take X at the generic point, we get a smooth manifold by assumption. Okay, so definition. An hermitian line model L bar equals L gamma the norm. It's a pair of objects L and an algebraic line model on X. So the first part. And the norm here is a smooth metric on the restriction of L on the complex point. So let's call L index C the restriction of L to the complex point of X. So we have the data, the algebraic data, which is a line model on the scheme X, and an analytic datum, which is the smooth metric on the corresponding holomorphic line model. We shall make some hypotheses, which I will not repeat afterwards because it's not very crucial. There is a map from XC to itself, which is a complex conjugation. And XC is a set of solutions in C of the equation of X. And if I have some coordinates, I can take their conjugate and we'll get another solution. So there is an involution on XC. So this involution acts on L. And we ask, that the norm is invariant under the evolution. As I say, I will not repeat this later. Okay? Now, we have a class which we denote C1 of L bar, which is the first short form of the holomorphic line model LC with the metric on it. So it's a class in A11 of XC. So the main result in the first talks I will give is the following result. There exists a unique way to define for every y in X closely reducible subset a number H L bar Y in the real numbers such that, well, there are two cases to consider. First, if the dimension of Y is 0, I think it is better to make a drawing. So spec Z has dimension 1, so we think of it as a line. And on spec Z we have X. Which is a projective flat scheme over Z. So a point of dimension 0 will map necessarily to a finite prime. So the residue field at this point of dimension 0 will be a finite extension of Z mod P. So the residue field, Ky, is finite. So for all subscheme of X of dimension 0, the residue field is finite, and we have HL bar of Y is log of the cardinality of this field. So it does not depend on L bar, actually. It's always the log of the cardinality of the residue field. So this is the case of dimension 0. And then we have a second condition, which is as follows. We choose a rational section of L on S on Y. Let S be a rational section of L on Y. So the divisor of this section is the sum of divisors in Y. Then we have the following formula. HL bar of Y equals the sum of n alpha height of y alpha. So this is what we will get in the algebraic setup, but there will be some analytic term, namely minus the integration of the set of complex points of y of the function log of the norm of S multiplied by C1 L bar to the power the dimension of the complex point of y. So we proceed by induction. For a point which is dimension 0, we have log of the cardinality. Now assume you know the height up to some dimension. To get the next dimension, you take y, choose a rational section, look at its divisors, this divisor, so the components are co-dimension one more, so we know the height of the component, HL bar y, and we define the height of y as the combination of HL bar y alpha minus this integral. So by induction, we have a way to define this real number, HL bar y. So we have the following remark. The unicity of this number follows by induction. Under the dimension of y. Because in this formula, y has some dimension and y alpha has dimension one less. So we know the height of y alpha, we can compute the integral, and the difference will give us the height of y. So we have a unique way to define the height of y satisfying this property. What is not clear at all is whether this definition makes sense, because we have many choices. Given y, we can choose any section on y, and then we get a divisor, we get a difference expression, and it's not clear that the difference takes the same value. So the difficult problem is to show that this definition does not depend on choices. In fact, there is some other difficulty. Which is that we have an integral here of log s on yc. It's not clear at all that the integral is defined. So we have a section, we have log of this section, and we integrate against the form C1 L bar to the dimension, and we take this integral on y. Yc is a singular variety, it's not a smooth variety at all. So it's not so clear how to define the integral. Fortunately, there is the following theorem. Which I will call theorem 2. And this is theorem by Yornaka. Which says the following: let X be a scheme of finite type of a C and Z in X a proper closed subset. Such that the difference X minus Z is smooth. So Z is taken in such a way that it contains all the singular points of X. Then there exists a map, call it pi, from X tilde to X with the following property. Well, first we have resolved singularities, so X tilde is smooth. Second, X tilde minus the inverse image of Z is the same as X minus Z. So to go from X to X tilde, we modify X, we blow it up outside Z. So the difference of X tilde minus the inverse image of Z is the same as X minus Z. And the third property is that Z is nice, so the inverse image of Z is a divisor with normal crossing. Say it again.
What do you mean by a divisor with normal crossing?
A divisor with normal crossing is a divisor written locally as product of Zi and I equals 0 for some local coordinate Zi. Okay? So assume we are in the situation I here. We want to define this integral. So we do the following. We consider Z to be the divisor of S and the support of the divisor of S union the singular part of Y. We look at some resolution of singularities. So let D be the dimension of YC. And consider a form omega of type DD on Y C minus Z. I claim that we can make sense of the integral over y of log norm s times omega. I mean, this integral is really the integral on y minus z. So it's an indefinite integral, but this indefinite integral is equal to some integral on y tilde of log of the inverse image of S times the inverse image of omega. So this is, if we wish, a definition. You define the integral on y as the integral on some resolution. Pi star omega is smooth on the smooth manifold y tilde. So let's assume that pi star of S is z1 to the n times u, where z1 star zd are local coordinates of y tilde. We can choose, I mean, if not, S, all S will be a product, S1, M1, SD, MD, and, but by, if I'm interested in log of norm of S, I get some mi log of zi. So the point is to be able to integrate log of absolute zi. So the form is equal to beta product dzi bar, where beta is infinity. And the integral of log z1 locally is the integral of log z1 pi star omega is the same as integral of log z1 dz1 bar times something bounded. So we concentrate on the variable z1. So I claim we can compute the integral because we have to integrate from 0 to epsilon log r dr d theta. If we take polar coordinate instead of z1 coordinate, we have log r dr d theta to be, and this integral is bounded because log r is less, goes to infinity, less and r goes to 0 faster. So this integral makes sense, and we can integrate log of s against C1 L bar by this technique. Okay. Qu'est-ce qu'il y a?
Je pense que c'est un bon endroit pour s'arrêter.
C'est l'heure?
Oui, pour le déjeuner, ils sont assez...
D'accord. Ok. Merci.